Gibson cloning is a molecular cloning method used to join multiple DNA fragments in a single reaction. This method has gotten popular since its discovery as it allows for precise DNA assembly seamlessly and without the need for multiple steps. Before diving into working example, let's go over what actually takes place during the Gibson isothermal reaction. To start, in order two or more DNA sequences to be assembled, they must have overlapping DNA ends, which are complementary to each other. Once the DNA fragments are prepared, the DNA is mixed with a reaction master mix that includes three enzymes that will drive three main enzymatic activities. First, exonuclease will chew back the 5' ends of the DNA fragments to create single-stranded DNA overhangs. This will result in two strands that anneal to one another. Next, DNA primers extends the 5' end, closing the DNA gaps. Lastly, DNA ligase seals the nicks in the backbone, forming a continuous double-stranded DNA molecule. Now let's have a look at an example workflow of all the steps you need to take from start to finish complete a successful Gibson assembly. In this example, we will have a look at all the steps typically taken to clone a gene of interest or a DNA fragment in a DNA vector. There are three major steps following with: 1. Linearizing the vector, 2. PCR amplification of the DNA fragment with overhangs, lastly setting up the Gibson assembly reaction. So there are two different approaches you can take to linearize your vector, either inverse PCR or restrictive digest. For inverse PCR, primers are designed around the interest site and amplify the entire vector backbone. For restrictive digest, enzymes are used to cut at the insert site to linearize the vector backbone. Personally, I find restrictive digest a lot easier to apply, especially when working with a large construct. So if you can take this approach, definitely recommend doing so. Just note, if you plan to linearize using only one restriction enzyme, make sure to use a phosphatase to remove the 5' in phosphate at the DNA end so that your vector does not reclose. Second is to amplify your DNA fragment using primers that will add DNA overhangs to your DNA fragments that are complementary to the ends of the vector. The best way to design this primer is using NEB's Builder Assembly Tool. I will walk through an example to show you how this can be easily done. Here I have an example of a vector and DNA fragments. Insert gene to design the right primers. I do a NEB Builder Assembly Tool with a link provided in the description below. To begin, process a new fragment and start by copying pasting the DNA sequence of vector to preview DNA. I like to use SnapGene Viewer, which is a free version of the SnapGene. Select all the copy, then press process. The text selected vector and circular. Here you can name your vector so you stay organized with your data, and then you will select the method that will be used to linearize your vector. As I previously mentioned, you may go to method is always restriction enzyme digest to find the appropriate enzyme to use. What you can do is go back to your SnapGene file. At the bottom, click on the map to see where you plan to clone your DNA fragment. Then you want to identify the enzymes that will cut at the site, and only at the site. You can identify these enzymes by clicking enzymes at the bottom and then from choosing enzymes at the top, select unique cutters. Go back to your map and you can pick the enzymes listed. I'm going to pick EcoRI and KPNI and add this to the NEB Builder Assembly Tool. Next, add new fragment. The DNA fragment that will be amplified and cloned into the vector. Process the text, name the fragment, select the method for production. PCR proceed. Here you can continue to add more DNA fragments or select done to receive an assembly summary where you will find the digested forward and reverse primer sequences. The final step to setting up the Gibson assembly reaction, which you will use to amplify your DNA fragment. The final step is setting up the Gibson assembly reaction. To set up the reaction, I recommend using NEB's assembly master mix. I provide a link in the description below. Here is the reaction setup you will need. Determine the optimal amount of the DNA of the insert and the vector to use in your reaction. Since we are cloning two fragments, it is recommended to use between 0.02 and 0.5 picomoles of DNA. As well as to optimize cloning efficiency, it is recommended to use 50 to 100 nanogram of vector within 2 to 3 fold smaller axis of the each insert. To help you measure DNA picomoles, you can use this equation or use NEB's BioCalculator link provided in the description. Below on the NEB BioCalculator, you can add the insert DNA length, the vector DNA length, and then add the DNA mass. For the vector, so let's say 100 nanogram. We saw that we want to use 2 to 3 folds, so let's say 3 folds. So that's 69.4 nanogram of the insert to use. To check the mass, go to mass to moles, and then length of the vector, and then add the mass that is used, so 100 nanogram, and you get the moles of DNA, which is 30.2 femtomoles, which is 1000 folds less than picomoles. Check the insert, add the length of the insert and the mass that was previously calculated, and you get the moles of the DNA, which is 9.61 femtomole, which is add up to the 0.12 picomoles. So that is within the range that is recommended. Once the mix is prepared, incubate the sample in a thermocycler at the 50 degrees Celsius, and it is recommended to do 15 minutes for 2 to 3 fragments, but I always keep my samples in for an hour just in case, so it is up to you, but I recommend 1 hour. Then following incubation, you can either store your samples on ice or at 20 degrees Celsius, minus 20 degrees Celsius, or subsequent transformations. Thank you for watching. I hope you find this video helpful. You have any questions, please leave them in the comment section below, and if you enjoyed this video, want to see more related content, don't forget to subscribe to my channel.